If I had to understand again why we needed this quantum mechanics, this is how I would teach myself. How did this almost impossible to understand theory even come into picture? In less than half an hour today, we are not only going to have a look at a simple problem which broke entire physics, but we are also going to dig deep and literally see exactly how did our super successful theories failed, and what exactly tipped the idea of quantum mechanics. While I will be showing some math here and there, the prime focus of this video is going to be visualizations and animations, which I made by writing code and putting in the same math which governs our reality. You know, sometimes the biggest, most world-changing revolutions in science don't start with some giant billion-dollar machine. They start with a really simple question about something you see every single day. Today we are going to talk about how the simple glow from a hot piece of metal managed to completely break physics as we knew it, and forced one very reluctant scientist to cook up an idea that would change the world as we know it. I mean, it sounds almost childishly simple, right? You heat something up, it starts to glow. But back in late 1800s, this simple everyday thing was a deep, profound mystery that the absolute smartest people on the planet could not figure out. And this wasn't just some little side puzzle. We are talking about a time when classical physics felt invincible. They had thermodynamics powering the entire industrial revolution. They had Maxwell equations which beautifully tied together electricity, magnetism, and even light itself. It really seemed like physics had an answer for pretty much everything, except for this. Not being able to explain why a hot object glows was this huge embarrassing crack in what was supposed to be a perfect theory of the universe. So, to really tackle this problem head on, physicists needed to simplify it. They came up with an ideal, perfect object for their thought experiments. They called it a black body. Now, don't let the name fool you. An ideal black body is a theoretical object that is a both perfect absorber and a perfect emitter of electromagnetic radiation. It's called a perfect absorber because it absorbs all radiation that falls on it, regardless of its frequency or angle, reflecting none. The term black in its name comes from this property, as an object that absorbs all visible light would appear black. The second property, being a perfect emitter, is linked to its role as an absorber through the concept of thermal equilibrium. According to Kirchhoff's law of thermal radiation, for any object in thermal equilibrium, the rate at which it absorbs radiation must be equal to the rate at which it emits it. Since a black body is an ideal absorber absorbing all incident radiation, it must also be an ideal emitter to maintain the thermal equilibrium. This means it emits the maximum possible amount of thermal radiation for any given temperature. The spectrum of its emitted radiation, known as black body radiation, is a continuous spectrum that depends solely on body's temperature, not its composition. But how come this led to the biggest blunder in physics? For that, we need to design an experiment. A pretty good real-world version is just an oven or a cube with tiny pinhole in it. But how does that work? Any light that goes into that hole just bounces around inside until it's totally absorbed. And here's the key, because good absorbers are also good emitters, the light that shines out of this little pinhole is the purest, most perfect form of this heat glow you can get. Which means the pinhole, not the entire cube, is almost an ideal black body. Okay, so now that they had these perfect theoretical ovens, the experimentalist could get to work. They could finally gather the hard data. They could measure with incredible precision the exact spectrum of that glow. You know, how bright each color was at all different temperatures. This data was the evidence. It was the crime scene that any theory was going to have to explain perfectly. And what they found was just fascinating. It was this very specific humped curve. It starts at 0, rises to a peak at certain color, and then drops back down to 0. But here is the truly amazing part. The shape was universal. It did not matter one bit if the oven was made of copper or gold or ceramic. The light coming out depended only on the temperature. That's it. That told them they were on to something really fundamental about nature. Now, physicists weren't completely in the dark. They had a few clues. The Stefan-Boltzmann law, for example, nailed the total energy. It showed that if you double the temperature, the object glows 16 times brighter. So things get bright fast. Then there was Wien's displacement law, which explained why the peak color changes as things heat up, going from red hot to white hot and eventually blue hot. But these were like describing the height and width of a building without having the blueprint. Nobody could come up with one single theory that explained the entire shape of that curve. So of course, they tried. Two brilliant physicists, Lord Rayleigh and James Jeans, took the best, most trusted tools of classical physics and aimed them right at this problem. And the results? Well, it was one of the most famous and spectacular failures in the entire history of science. Their approach was perfectly logical, totally by the book. Step 1. They pictured that the black body cube being filled with a zillions of light waves all bouncing around, like standing waves on a guitar string, one for every possible frequency. Step 2. They applied a rock-solid rule from thermodynamics called the equipartition theorem. All it says is that when things are in thermal equilibrium, every single one of those waves, no matter its frequency, should get the exact same slice of the energy pie. Made perfect sense. It was solid physics. I mean, what could possibly go wrong? Well, the result was a complete and utter shock. At low frequencies, the infrared and the red part of the spectrum, their theory matched the data perfectly. It looked like they'd cracked it. But then as they moved to a higher and higher frequencies, or lower and lower wavelength, into the ultraviolet part of the spectrum, the theory just went completely insane. It predicted the energy would just keep going up and up and up, all the way to infinity. This epic failure got a very dramatic name, the Ultraviolet Catastrophe. Their theory predicted that every warm object, your coffee cup, a candle flame, you and me, should be blasting out an infinite amount of energy, mostly as deadly ultraviolet rays and X-rays. This wasn't just a little off, it was absurd. It broke the law of conservation of energy. Classical physics had just slammed face first into a brick wall. But what exactly went wrong? How did we get an infinity here from our super successful theories? Let's first understand it a little bit in more depth. The issue is so absurd it will surprise you. And from that absurdity, the entire branch of physics, known as quantum mechanics, was born. Let's get inside the cube to see what exactly happens when the light enters the cube via that hole. Inside the cube, after entering from the hole, the light gets reflected from wall to wall. That creates something called standing waves, and that is our first step. Let me show you how does that look by looking a cross section of our cube here. And yes, before you ask, standing waves are also present in musical instruments like guitar. But hang on, how does a wave stand? Let's imagine a typical traveling sine wave going to the right. This is how we can describe it in equation. The minus sign in the equation is telling us that if you let the time flow, this wave will travel to the right. Similarly, we can define a wave which is traveling to the left. Notice that minus sign is now a plus sign. But what happens when both of these waves meet in the same region of space? Like on a guitar string, the waves will superpose and the net amplitude is simply the sum of two individual waves. When you sum up these two equations and apply some basic trigonometry identities, you get this expression here. Now the fun part. Here is how it looks when superposition happens. As you can see, when we sum up both right moving and left moving waves, the resultant wave looks something like this. And it is also clear why is it called a standing wave. Now let's apply this to our cube. Our cube here is three-dimensional. We can analyze our electromagnetic wave reflection back and forth in three components of x, y, and z. Let's reduce one dimension and have a look at the xy plane. And this here, what you are seeing, is how a standing wave looks in a plane. This is important and we will be back here. But first, it will be easier to understand in just one dimension. So let's start with just x component. Imagine that these two are the walls of the cube perpendicular to x component of the wave. And since the wall is perpendicular to the wave component, the electric and magnetic field displacement will be parallel to the wall as per the definition of light being a transverse wave. But since the wall is metallic, it has free electrons which can freely move when induced by an electric field, just like a current carrying wire. That means at the wall there cannot exist an electric field parallel to it. And if there is no electric field, means there is no electromagnetic field, aka our light waves. That means at the walls the amplitude of our standing wave must be zero. This is what we call a node of a standing wave. And similarly, antinode refers to the point of maximum amplitude. It looks like there is a rope tight fixed on both walls at these points, and it's just vibrating, exactly like a guitar string. And this boundary condition put a restriction on the possible wavelengths and hence frequencies we can have in our cube, because the same thing applies to y and z components as well. When you apply these boundary condition and do the math, you reach this equation for the wavelength. This means our wavelength and frequencies can only take certain values bounded by this equation. We can try and see what it looks like. Between the walls of a cube, here are some of the different allowed wavelengths and their respective waves. So why are we studying these different combinations of waves? Well, what we are interested in is the energy distribution. But energy distribution among what? The answer is what we call degrees of freedom. But what the heck is that? So before we understand how our energy shoots up to infinity, let's visualize degrees of freedom first. In physics, the degrees of freedom of a system is simply the number of independent ways it can move or have energy. Imagine a point particle floating in space. To know exactly where it is, you need to know its position in three directions: up, down, left, right, and forward, backward. That's 3 degrees of freedom. Now imagine two atoms bonded together, like a tiny dumbbell. It can still move through space in those 3 directions, but now it can also rotate. It can spin end over end in 2 different ways. Again, from different angle, 2 different ways. Spinning along the axis of bond doesn't count due to extremely tiny moment of inertia. So this molecule has a total of 3 plus 2, 5 degrees of freedom at a given temperature. If you add a lot of energy to that molecule by heating it up, the bond between the two atoms can start to stretch and compress, like a spring. This back and forth motion is another way a molecule can have energy, and it adds up 2 more degrees of freedom. One for the kinetic energy of the motion and one for the potential energy stored in the spring-like bond. So at very high temperatures, it has total of 3 plus 2 plus 2, 7 degrees of freedom. We can calculate the number of such degrees of freedom of a standing wave. But this is in one dimension. As you can see, there is no frequency term here. Means when it comes to 1D, the degrees of freedom does not depend on the frequency. However, when we do the math and extend this to 3 dimensions, we get this equation. And here you see there is a frequency term which is squared. That means the degrees of freedom increase rapidly with high frequencies or shorter wavelengths. And here is another twist. Our cube can contain ever increasing frequencies as long as we have 2 nodes at the wall. And now the final piece of the puzzle, which is going to lead us to the predicted infinity. And then we are also going to see why we needed quantum mechanics to explain it and save the day. Let's say that we have a party and only way to feed people in the party is to give them all a pre-packed plate of food. So everyone equally gets 1 plate each. This is what known as equipartition theorem. It simply says everyone gets an equal share. But you quickly realize that we just saw how our cube system has infinite degrees of freedom, and if you give 1 plate to everyone, you will need infinite plates. In this analogy, people in the party are the degrees of freedom, and the food in the plate is the energy share per degree of freedom. And thus you see how our super successful theories predict infinite energy in any radiating object. And this was ultraviolet catastrophe. So how exactly quantum mechanics solved it? Max Planck, while working on this black body radiation, solved this issue by this simple trick, what he later called an act of desperation, and honestly did not like his own theory. He was trying to do something, anything in the math, so that the theoretical curve matches the experimental curve. How exactly did he do that will require its own separate video, but this is what he did. He said that the people at the party are not all equal. He said that some of the people are kids and rest of them are adults. While the kids can have their fill from that 1 plate of food and thus they accept the plate. However, adults require more energy and that plate of food is simply not enough to excite them. So the adults simply don't take the food. So you see, after a certain age, most adults will not consume any plate of food, preventing the infinite amount of plates. Coming out of that analogy, Planck introduced the radical idea that energy could not be emitted continuously but only in discrete tiny packets. He proposed this formula. It meant that high frequency modes, which required a large quantum of energy, were rarely excited. This prevented the infinite energy prediction and correctly matched the observed curve. Planck called these packets of energy quanta, and thus quantum mechanics was born. And in quantum mechanics, there is a huge myth about the uncertainty. People think that things are uncertain before you observe them, but once you throw light on it, the uncertainty goes away. That's not the case. Click and watch this video here to truly understand what Heisenberg said in his uncertainty principle.